Okay, so the topic of today's lecture is feature detection. So features are really important for all sorts of computer vision problems, and they're definitely important for lots of under-the-hood visual effects problems. And so I guess the first question is, what is a feature? So a feature basically is a place in an image that I can kind of unambiguously recognize if I see another image of the same scene, possibly taken from a different perspective, right? And so, the broadest definition would be something like, recognizable, or I'd say repeatably recognizable regions in an image. And so I'll show you a couple pictures to illustrate what I mean. So for example, here's a picture of a scene, okay? And so everything in this chapter is going to be grayscale just because a lot of the machinery is, assuming there's only one color channel. You can do all the stuff I'm talking about in full color if you want to, but at least for the purposes of explaining things, I'm going to talk about things in grayscale. So, suppose that I took this picture and I took a picture of the same scene from a slightly different perspective. What would be good places that I could choose features at in the hopes of identifying the same 3D point from a different perspective? Well, so, suppose I chose, something right here, right in the middle of this flat space. Well, that would be a pretty bad idea, right? Because this flat space matches up with pretty much all the other similarly flat gray places in the image, right? So I couldn't really unambiguously say, this point in image 1 was exactly the same as this point in image 2. That's what we need to find at places where we can't have any error about where the feature is. So you might think, okay, well, so what I should do is I should find places where the image is kind of busy or edgy, right? Again, that makes sense. So here's a place where there's a nice edge, right, between this post and the floor. And again, if I were to choose a feature right on the edge of this post, that's a little bit better in the sense that I couldn't confuse it with something that was on the floor or fully on the post. But at the same time, that feature could kind of slide up and down this post, right? Because there are lots of places that look like the same post to floor boundary, okay? And actually that's something that we call the aperture problem in computer vision. That means that things are okay in one direction but bad in another direction, okay? So what would make good features? So a good feature would be something like this sticker up here on the post, right? So it looks like this little circular sticker. I'm going to zoom in on these things in just a second. Why would this be good? Well, there's nothing in the local neighborhood of the sticker that looks anything like that sticker, right? So if I drew a box around that sticker, there's nowhere else in the image where something that really looks like that box appears, right? It would be really only that one place where I originally had my feature. Similarly, something like the corner of this rectangular sticker would also probably be pretty good, right? That corner has some locally distinctive stuff. There's this Japanese character, there's the shape of the white corner on the post background, and if I were to draw a box around that, there's nothing in the image that would look exactly like that anywhere else, right? And so let me just zoom in on these possible features, right? So I'm saying that this is bad because it's basically an empty area. This is bad because it can slide up and down the post, and these two guys here are pretty good. And so this is kind of zoomed in. This is why these are bad features, right? There's recently in the post, there's not enough edgy texture variation to make this a good feature. Here, there's a nice edge in one direction, but not in the other direction. Here is an example of a good, nice corner, right? I can't slide this box around and get something that will match exactly to this corner, and the same with this sticker, right? And so what we want to do is mathematically formulate the properties that make a good feature. And then we want to design an automatic feature detector that I can take an image, and I can run this feature detector on the image, and I can find a bunch of good features that hopefully I can match up when I see that scene again, right? And so as you can imagine, this process of finding and matching features is really important for any time where we have to match two images together for some purpose. And one of the key visual effects scenarios is a problem called match moving or camera tracking, where as the camera moves through the scene, I want to know where in 3D space did this camera move. The whole foundation for that technology is based on tracking features, right? So we start with the apparent 2D matches between places that we've said are the same place in both images, and then we estimate the 3D camera path. So that's the subject of chapter 6. So to lay the groundwork for that, I want to first start talking about what makes good features. And so probably everyone in the room has already heard about what are called SIFT features. So SIFT features became very, very popular in computer vision recently. We're going to talk this morning at the end of class about the foundation for how those features are detected. And then we're going to talk about the matching process in the next lecture, right? So basically there are two pieces to features. The first one is what makes a good feature and how do I find them? And the second one is how do I describe the pixels around that feature in a way that they can be matched unambiguously between two images in the same place. And so I'm kind of breaking it up into detection and description. So today is mostly about detection, although there'll be a little bit of extra detection on the next lecture. And the next lecture is mostly about description. Okay, so basically, flat or regions that look like this, for example, are bad because the matching is going to be ambiguous. Corners and blobs are generally good, right? So by a corner, I mean something like what I drew here, right? This is kind of like what I drew in the actual image. And a blob is something that's more like this, right? And so one thing to keep in mind, right, is that when we do feature detection, right, you might imagine that if I'm looking out at this classroom, I could say, oh, well, I could detect all the people's faces, right? That would be something where I could say, oh, I can match this guy to this guy in the same image. When we talk about feature detection in image processing and computer vision, we're generally not trying to find things that are kind of semantically meaningful, like faces or computers or books, right? We're usually finding pixel patterns that in themselves look kind of random. I mean, like you as a human would not necessarily pick out these blocks of pixels as being like something you would recognize, but for a computer vision algorithm, it turns out that those pixels are mathematically good places to match, right? So the features that we're going to generate in this section are not really kind of human interpretable things that you would say, oh, these are really sensical features, right? Some of them may look like, why did it choose that? Well, it turns out it was just mathematically good, right? You see that especially when we talk about things like SIFT features. Like, SIFT features don't match up at all often with human perception of what a good feature should be like. Okay, so what is a way to formulate this concept of a good feature? Okay, so how to mathematically formulate. Well, I'm going to exactly follow the intuition that I said earlier. Right? A good feature is one such that if I draw a little box around that feature, I shouldn't be able to move that box locally around the feature's location and get a good match, right? So what does that mean? So that means I can make it kind of like a cost function. I can say, consider a small block of pixels around a candidate feature location x comma y. All right, that's like saying, okay, here's my image, here's my possible feature location, and here I'm drawing a box around that feature location. And now what I'm going to do is I'm going to say, okay, well, what if I were to compare this box to a slightly shifted box, right? And I want to find the error, like the sum of square differences of pixels between those two boxes, right? So kind of what I'm doing here is it's like saying I'm moving the box along a vector, and the vector here could be like u comma v, right? So that's kind of like saying I'm comparing. So here we're going to get a little bit hairy. So what I'm going to do is I'm going to say, okay, I'm going to sum over all the xy in the window the difference, or let's say the sum of squares, between the pixel here and the pixel that I would get if I moved the box by this vector u comma v. Okay, so maybe to make this a little bit clearer, what I would do is I would make, to distinguish from here, let's say that my original feature location is like x0, y0, right? And then this window is centered at x0, y0, right? So x0, y0 is like a fixed location that I'm considering, and now looking at all the xy's that are within a local neighborhood of that x0, y0. And all I'm doing is I'm saying, for all the people in the window, let me compare pixels in corresponding locations, right? And what I would like is for that number to be small, okay? So basically, this should be small for any UV for this x0, y0 to be a good feature. Right? That's like saying that locally, I shouldn't be able to push that block in any direction and get a low value of this measure, right? Because if I could, that would mean that if I move the block in that direction, the feature would look basically the same, right? So this would kind of like be saying, if I consider, this kind of block, well, if I moved the UV in this direction, life would be fine, right? Because I would get a high difference between this block and, something like this block, right? Because there would be lots of black and white pixels that didn't match up. But if I looked at pushing the block in this direction, life would be bad, right? Because that's the aperture problem where I couldn't really tell the difference between sliding the block up and down, right? So this is kind of like saying there should be no UV such that moving the block around will cause me any problems, okay? All right, so let me pause and ask a question.
So do we evaluate this for all possible values of U and V?
So we don't actually explicitly evaluate it for all possible U and V, and I'm going to show you how we get around that in a second. But basically, what we're going to do is we're going to form a 2x2 matrix that is built from all the pixels in the window, and we're going to use that matrix to help us decide whether it's a good block or not, right? So yeah, we don't have to actually explicitly characterize this for all the U and V. I'll show you how that works in a second. Question?
So for it to be a good feature, you want a large difference when you shift it, right?
Yes.
In any direction. In all directions. So why does it say that?
Oh, did I screw this up? This should be, large. Yes. Sorry, yes. My mistake. Other questions? Okay, so this is the kind of principle, okay? So, and I can assign this a name. I'm just going to call this the cost of moving in the UV direction, okay? Okay, so how can I make this a little bit easier? Well, this basically is related to the gradient of the image. And so those of you who have taken some image processing know that there's this kind of, so just similar to what you just found out for the Poisson homework, right? So in image processing, we typically have kind of continuous style notation where I've got like a partial of the image in the X or Y direction. That's kind of assuming the image like a continuous grayscale, there's no pixelated image. It's like saying the image is like a continuous, blanket of intensities, right? And then usually to do real world MATLAB stuff, we have to turn that into a discrete thing like the Laplacian with the 4s and the -1s. That's like a discrete version of some continuous derivative operator. And so I'm going to kind of do the same thing here. So what I'm going to do is I'm going to say, let's expand this thing in a Taylor series about UV equals 0, 0. What this is like saying is, suppose I were to take the directional derivative of the function in, going a little bit in any direction, right? So that means that my cost function is basically like the sum, again, over all the pixels in the window of, well, what is the first part? First part stays the same. And then the part that used to be here, x plus u, y plus v, I can approximate as basically the original image plus u times the gradient in the x direction plus v times the gradient in the y direction. right? That's kind of like saying that my, you know, well, I mean, if this doesn't look familiar from a Taylor series, then you kind of have to go back and look at calculus to remember how Taylor series work, right? That's kind of like the idea, is it's saying I want to approximate the function at a new point by using the functional value at a point that's kind of close by, and then stepping a little bit, you know, having a little bit of a correction factor that says how much am I different from this original point. And so if I kind of were to simplify this, you can see that these guys drop out, and what I get is this thing. And if I expand this out, I'm going to get this thing. And then I'm going to cleverly rearrange this into a 2x2 matrix like this. Remember, this kind of thing that looks like a 2 here is actually a partial derivative. So you can basically convince yourself that if I were to multiply this out, so this is a 2x2 matrix, this is a 2x1 vector over here, and this is a 1x2 vector over here. So when I multiply all this stuff together, I get a 1x1 number, and that's the cost. Question?
Why are you assuming that the second derivatives are negligible?
Well, that's exactly what I'm doing with the Taylor series, right? Is I'm dropping those terms of the Taylor series.
That might not hold true in actual.
Right. So the question is, why can I drop the second derivatives? Well, that's a good question. I mean, and we will talk in about 20 minutes about detectors that use the second derivatives. So we'll kind of come back to that, right? So basically, this is like a first order derivative. Yeah. So you're going to lose some stuff by losing the second derivatives, but what can you do, right? As with any Taylor series, right? That's the way Taylor series work, is you have to decide when do you stop adding terms. Okay. And so now the question is, okay, so this matrix here that I'm going to draw, I should have brought a different colored pen, that I'm going to draw in this box here, plays a very special role, right? So this is basically saying, let me be explicit. So I can take the u's and the v's out. So I can build this matrix I'm going to call H, which is fundamentally the following. Right, so this is like saying that so this sum, all these sums are over the window around the pixel that I'm kind of asking my question about. And so what I'm doing is I'm basically building this 2x2 matrix of summed gradients inside the window, okay? And this we're going to call the Harris matrix. So if you have ever heard of the Harris coronary detector, that's what we're talking about. So if you ever go into OpenCV or something like that, you're going to see something that's like the Harris coronary detector. That's exactly what we're talking about here. So what do? I have a candidate for a feature, x0, y0. I build this 2x2 matrix. Now what do I do with the matrix? Okay. Well, what I'm going to do is, I would use the matrix here to build a cost function in any direction. And so before I talk about the matrix, let me just look at this for a second and think about, okay, so what would this EUV look like as a function of direction for the blocks I showed you earlier? So here's this example. So again, the first two are the bad blocks, right? So this one is basically saying, okay, a flat block should have basically low kind of goodness in both u and v directions. That's like saying that I can move basically in any uv direction and still get fundamentally the same feature, right? So this is bad in all directions. This one you can see is really bad in one direction, right? So there's a direction that corresponds to the orientation of this edge that says if I move along that direction, my E is almost 0, but if I move side to side kind of across the edge, then I should be at a lot of cost, right? And then these guys here, the key thing to take home is, number one, that the values of E are very, very high as soon as I move away from 0, 0, right? So this looks like, I mean, ideally you'd like it to look like a bowl, right? Where as I move away from 0, 0, I get increasing cost. Here, these guys are really good in the sense that that looks like a spike almost, driven down to 0, 0, where actually, really, I raise cost almost immediately as I move away from that feature. That means that these are very good features, okay? So now let's talk about what these numbers mean, right? So these numbers here are related to the eigenvalues of this H matrix. So let me just come back to this. So using H to find good features, well, you know, it kind of comes down to, and I don't want to, again, this is something where you kind of have to remember some eigenvalues and eigenvectors. So basically, what would it mean if there was a direction, uv, such that if I moved in that direction, I basically had a low cost? That would kind of mean that uv was close to a 0 eigenvalue or a small eigenvalue in some eigenvector direction. So what I want to have is a matrix that has high eigenvalues. That means that there's no direction such that if I move in that direction, multiplying the h by that uv gives me something close to 0, right? That's kind of the intuition. So, and the book goes into a little more detail about exactly, so let's suppose, just to take an example, so let's suppose that I have an entirely flat block, right? So if I have a flat block, then basically all these numbers are fundamentally pretty close to 0, right? That means the eigenvalues are also going to be pretty close to 0. If I have a, if I have a block where one of these guys is close to 0, let's suppose that, di dx is close to 0, but di dy is not, right? That means that moving the x direction, I basically don't have any change. Moving the y direction, I have a lot of change. Well, that's going to mean that 3 of these numbers are going to be 0, and the other one is going to be high, right? That means that one of the eigenvalues is going to be basically 0, and the other one is going to be big, right? So what I want, in some sense, is both the eigenvalues to be big. And so the original Harris idea is the Harris quality measure is to take the determinant of H minus some multiple times the trace of H. Remember, the determinant is what we get if I take kind of like, that's like saying I have AD minus BC, and this is like saying I have minus this trace. You can show that this is related to the eigenvectors. And what I can do is basically, this is going to be small when one or both of the eigenvalues is small, and big otherwise. Another possibility is to do what's called the Tomasi, or sometimes called the KLT detector, which is just basically to take the minimum of the 2 eigenvalues. So either way, what I'm doing is I'm building this threshold, and I'm building this measure, and I'm saying, give me all the pixels such that this number is bigger than some certain value, right? The Harris one computationally is a little bit easier because I don't actually have to compute any eigenvalues, right? I can just compute stuff straight from the matrix itself, whereas for this one, I actually have to compute eigenvalues, which is not like super burdensome or anything. It's a 2x2 matrix. You can do it pretty easily. And so if you look at the guys here, what I'm showing you are the eigenvalues and the corresponding Harris cost. And so you can see that here, the flat block has 2 eigenvalues that are very small, and the corresponding cost, the Harris cost, is very small. here, this guy has one big eigenvalue, one small eigenvalue, but the Harris cost still turns out to be small. And these guys both have robust eigenvalues in both directions, and the cost function is very large. And so what I could do is I could say, okay, run this cost function across my whole matrix, or my whole image, and find me places where C is greater than 25, right? Tell me those pixels, and that will give me good corners that I can use for feature detection, right? And if I do exactly that, what I get is a picture that looks something like this. And so you can see that the blocks that are coming out of this detector are not sitting on blank regions of the image. They're not sitting on edges. They're sitting on kind of edgy, cornery regions, right? So for example, it did pick up the blob that I showed you before. It picked up the corner of this poster I showed you before. It's picking up lots of stuff in the trees, which we may or may not be able to use. But anything where there's like a nice edge that's happening in both directions, this detector is picking up on, right? One thing that I also did to make this image was you'll find that when you run this detector, that a lot of times you get, if one pixel is pretty good, then its neighbor is also probably a pretty good feature also. And so the idea is that what you can do is you can kind of do what's called non-maximal suppression, which says, okay, for you to come in as a feature, you need to be a better feature than anyone in your local neighborhood. That way you don't get features that are like all crammed together in one place. And so in MATLAB, you can do this with, there's a corner function. So if you do help corner, you can see that there's actually exactly what I just showed you, right? So here, there are two methods that are built into corner, the Harris corner detector and minimum eigenvalue, which is the one I put at the bottom of the last page. And so, that's pretty straightforward. Oops, sorry. Okay, so let me ask, questions or comments about that? All right, so now it gets a little bit hairier, okay, because in practice, we're going to layer on a couple of twists to this that make the detector more general and more useful, but also more mathematically crummy. Okay, so we're going to have a little bit of math to wade through in a second here. Okay, so the first thing is, and it's all intuitive, but it may take you a minute to kind of think about why these things make sense. So the first thing is that we really care about the pixel in the middle of the block, right? That's the feature that's the place that we're trying to decide, is this place a good feature or not, right? And so it's kind of natural to imagine that what I want to do is consider the pixels that are closer to the middle of the block to play more of a role in making a decision than pixels that are at the very periphery of the block, right? So instead of treating every pixel in that block equally for the purposes of this cost function, what I could do is I could weight the ones that were in the middle a little bit more, right? That's like saying that I really care about the stuff that's happening right around the feature, but I could care less about the stuff that's happening right around the periphery of the block, right? So that's like saying that instead of, if I were to kind of think about kind of an importance function, and this is the kind of footprint of my block. So the old method is basically saying, in terms of importance, all these guys are equally important. Instead, what I want to do is I want to say, okay, well, this guy should be more important than this guy and a lot more important than that guy, right? So that would argue for something that looks more like a nice gradual fall off around the pixel that's in the middle, right? This is like you can imagine that I weight my contribution with a Gaussian window, okay? So immediately we have this kind of Gaussian thing that's basically saying, okay, so instead of building this matrix here that has all the sums, so that's like saying that if I have my xy in the window, originally I had this term. What I would do instead would be I would put a weight here, right? That's like saying that for every xy, I have a weight, and this weight is something like a Gaussian that is centered at the pixel of interest. And that Gaussian has a certain scale, right? That basically says how peaky do I want this Gaussian to be around the middle, right? And so this is a Gaussian. And I'm going to kind of call that the kind of integration Gaussian, right? Because what I'm doing here is I'm summing up a bunch of things, right? So this is kind of like similar integration. It's like saying, okay, well, over what region do I really care about pixels around my block, right? In fact, I could almost throw out this, window entirely. I could just say, okay, well, I'm going to build a Gaussian around every possible location, and at some point when that Gaussian is too small, I just throw away those pixels entirely, right? And so, if I really care about only really local behavior, I use a small sigma. If I really care about big behavior, I use a big sigma, right? Okay. So that's one idea, and of course this kind of happens in all the pieces of the matrix. I'm not going to do it for all that. So the other kind of tricky part comes in terms of how do I build these derivatives, right? So right now I've kind of kept everything in the continuous world, but so those of you that have done image processing know that there are many different ways to compute, for example, x derivatives in an image, right? So if I wanted to compute kind of like the left to right derivative, right? One thing that I could do is I could just use this simple operator, right? But you may have also heard of an operator that looks more like this, right? This is called a Sobel gradient operator. And so what's the difference between this edge operator and this edge operator, right? When do I want to use one over the other? Because a lot of times if you do image processing, people will just say, oh, I just use the Sobel edge filter, right? What does that mean? Well, this thing I can think of as fundamentally a vector like this multiplied by a vector like this, right? So that's like saying here, this is the part that is the derivative, and this is kind of like something that is smoothing in the other direction. Sometimes why I want to do this is I want to kind of smooth out the image prior to taking the derivative, so my derivative is not picking up kind of noisy bits of the image, right? I want to kind of get the true underlying differences without having to deal with stuff that might be due to noise. And so what I could do is I could smooth the image prior to taking the derivative, and my derivatives would be in a hand-wavy way more accurate, okay? And so I could go even further, and what I could do is I could say, so this is, I'm not even sure if this has a name. It's called super simple. This is Sobel. I could also do basically even more smoothing before I take the derivative. And what I could do instead is I could take the derivative of the Gaussian. What I mean by that is that I could approximate my derivative like this as the image convolved with the derivative of the Gaussian. So again, this here is a Gaussian in the x direction. Or if you like, I could think about basically convolving the image with the Gaussian first and then taking the derivative, right? So it's kind of like I'm smoothing before I'm taking the derivative, right? So this is a smoother way of taking derivatives than this, okay? And so now we have another Gaussian at work, right? This Gaussian is basically saying, well, how wide should that sigma be in order to take the derivative, right? And so we would call this the derivation Gaussian, or the derivative Gaussian. Okay, so now we have basically two parameters that I would need to specify. One tells me what is the width of the window here that I'm using, or what is the width of the Gaussian here that I'm using to take my derivatives, and the other one is what is the width of the window over which I care about, pixels contributing to my, feature detector, right? So if you look in the textbook, you see all the gory details about how all these things take the original Harris matrix and turn it into something that looks a little bit more, a little bit more messy. Okay, so let me pause and ask about. So why did I introduce all this additional complexity, right? So one reason to do this, as I'll show you in just a second, is that a drawback of Harris corners is that I have specified the size of the box that I care about, right? So when I do MATLAB Harris, MATLAB is making a choice about how big these little boxes are, and they're all the same size, right? And if I don't like, and how would I choose the right size, right? How do I know that a 9 by 9 block for features is better than a 13 by 13 block? I don't really know, right? So the idea here is that what I would like to be able to do is what I would call multi-scale features, right? Where I would say, okay, let me find boxes that could change in size, where maybe if I had, something like this, where there was a huge corner, maybe I would find a huge feature that says, hey, this feature is really important at a very large scale, right? This is a large scale feature. And if I had a little blob like this in the image, then I would find features that said, hey, these are features that are significant at smaller scales, right? So in some sense, what I could imagine doing is taking my Harris detector, and I could just change the size of the block, and I could iterate looping around the size of the block, and I could find features that were significant at different scales. But that seems a little bit clumsy to do, right? In some sense, I want something that's kind of automatically going to figure out what should the inherent scale of a feature be from the get-go, right? And so to use this kind of idea of multi-scale, that's kind of why I've introduced this pair of Gaussians, because there's this whole rich theory that I don't really want to talk about in a lot of detail because it's very complicated, called scale space theory, that kind of says, what happens when I keep on taking derivatives of an image. So if you remember, this is not unrelated to the Gaussian pyramid we talked about a couple weeks ago, right? So we were talking about in the context of compositing, right? We talked about how you could take an image, you could keep on smoothing it and downsampling it. We called that a Gaussian pyramid. So here, what we're going to see in this case is that you can kind of think about some stuff involving feature detection in the same way, where I take an image and I keep on smoothing it and finding features at different smoothing levels, right? So features that still remain in the image after I've smoothed and smoothed and smoothed are things that are more like this, things that don't go away when I keep on blurring the image, whereas features like this will go away after the first smooth, right? So they're significant at a smaller scale. That's kind of the idea that I want to convey. So there's like a spatial scale that comes along with every feature, okay? All right, so let me pause for a breath. So that's where we're going. Questions about that? Okay. All right, so now I gotta get ready for the really dense part here. Okay. So let me try and write down, kind of condense what I just said, is that, regular Harris corners are defined at a single fixed scale. We want multi-scale features and each feature should come with a kind of a natural scale. Okay. And so let me just kind of show you a preview, and we're going to come back to this picture in a second. So the preview is the following. Okay, so let's suppose I want to look at this bird in a birdhouse. Okay, so I have the original image and I have the zoomed in image. Okay, and so what I would like is something that operates in this way, where if I were to put a feature on top of the bird, that the circle that comes with it is basically the feature detector automatically telling me this is the scale at which this bird is significant. Okay, and if I zoom in, the circle maintains its apparent size, right? So when I apply that same feature detector to the zoomed in image, the circle that comes back is physically bigger, but if I think about the kind of image terrain that is covered by the circle, it's the same in both images, right? This, if I could do it, would be promising in the sense of letting me match images that didn't have exactly the same zoom level, right? So if I had an image that was zoomed in, an image that was close up, or an image that was far away, I should be able to find matching features even if the physical pixel extent of the feature is much different in these two images. Okay, so what I would call this circle type behavior would be a kind of scale covariance. Okay, so kind of what we want is called scale covariance, which should mean that the apparent scale of the feature, changes correctly with zoom. That's a very hand-wavy way of saying it, but that's kind of what I mean, right? So think about the bird, right? I want to make sure that the same pixel terrain is covered by the apparent scale of the feature in both cases. Okay. Okay. All right, here we go. So, key concept. Apparently this is paper from before. So the key idea is what's called scale space. Is the scale space of an image. Okay. Now, let's not overthink this. Okay, so what this really means basically is that what I'm going to do is I'm going to define a new image as a function of a scale, we call that sigma 0, that is nothing but the original image blurred by a Gaussian at a certain scale. So this is basically like the original. This is a Gaussian blur, and this is a blurry image. Okay? So the bigger the sigma, the more blurry the image is. Okay? And actually, let me make, instead of calling this sigma 0, we call this sigma d. Okay? So I can rewrite the Harris matrix in the following slightly messier way. Okay, so now my Harris matrix, add a pixel xy, and I have two Gaussian scales to worry about, right? This is the derivation scale, and this is the integration scale. So this is just rewriting the stuff I talked about earlier. So this is like saying what I could do is I could take the derivative of this dx squared and then I also have like this derivative and this is convolved with a Gaussian at the integration scale, right? So again, let's think about what all these numbers mean, right? This is like saying that here, what I'm doing is to compute the x and y edges, the derivatives, I have to specify how big the Gaussian is that I want to convolve it with. That's what this sigma d is. And then this sigma I is now playing the role of the window, right? So instead of having a specific sum over a certain window, all I'm doing is I'm letting the Gaussian play the role of the window, right? So if sigma is small, the window is small. If sigma is big, the window is big. Okay. Okay. And so, question.
Yeah, just quickly. So we always want to use a radially symmetric Gaussian.
Yes. Yeah. All the Gaussians here are definitely radially symmetric.
Is
Yeah.
that because like anywhere, any direction we go?
Yeah. I mean, it would be kind of weird to not use a symmetric Gaussian for this purpose, right? We want kind of uniform blur in all directions. There's no reason to have a non-uniform Gaussian. Yeah.
Yeah, I think that makes sense.
Okay, I hope it makes sense. All right. Okay, so remember that what I want to do, right, is I want to find places where this H matrix is large, right? Places where the, where the eigenvalues of the H matrix are large, right? So it kind of stands to reason that the more stuff that I add into the window, right, the bigger the integration scale, kind of the bigger the eigenvalues will be just by virtue of the fact that there are bigger numbers in the matrix, right? So the more stuff I add into the window, then naturally all of my, so if I want to, so what I'm getting at is if I want to compare the measure here versus the measure here, right, centered in exactly the same place, inevitably the measure here for the bigger box will be larger because I'm including more stuff in there. I'm adding more derivatives in. Basically, it's like I'm including all the stuff that was in here plus all this extra stuff, right? So the number is bound to be bigger, and I don't want the fact that the window is bigger to automatically bias me towards saying those big windows are great, right? In some sense, what I have to do is I have to normalize my number with respect to how big my window is, right? That's kind of what I want to do in this step, is to say, okay, so when I compute my Harris matrix, what I want to do first is normalize it so that I'm comparing apples to apples at different scales, right? What I need to do is I need to divide this matrix by some factor that will take into account that behavior. And so the long story short, so this is slightly chickening out, but just because it's a lot of derivation to repeat, So what I want to get at is that what I do instead is I build what's called a scale-normalized Harris matrix. So I take the, so here's kind of what I want to say. Let me write this down first and let me explain what it means. Okay, so what I'm going to talk about here is that I have high res so that means I've got a big image, and over here I've got a low resolution. This is not the way you spell resolution. So I have a smaller image, right? And I want to ask myself, okay, so let's suppose that my xy coordinates here and my x prime, y prime coordinates here are related by this. This is like saying that, for example, if k equals 2, that's like saying that this image is twice as high resolution as this image. Okay. So pixel 100, 100 here corresponds to pixel 50, 50 over in the low resolution image. Okay. So that means that there's a matching up between every pixel coordinate between the high res and the low res, right? And so k is kind of like my scale factor. And now what I want to know is, if I take a pixel here and I look at the corresponding pixel over here, and then I look at a region over here that is k times as big as the region over here. So the idea is that these two circles are encompassing the same stuff, right? The same apparent image stuff, right? And what I need to do is, to make this directly comparable to this, I need to divide by my scale squared. So this is basically a way of saying, okay, if I want to directly compare the response at a certain scale here and the response at a certain scale here, this tells me kind of like the normalization factor that I need to compare apples to apples. So what it comes down to is that when I look at, in the spirit of not having to draw all this again, so if I come back here, this is kind of like my original Harris matrix. It turns out that what I need to do is I need to multiply this by k squared to obtain the scale normalized Harris matrix. What this means is that this way, the responses that come out of this operator are all scaled to kind of a uniform, y-axis, so that I can now say, okay, tell me everything that is important above a certain threshold, and the features and the scales that come back are all going to kind of match up no matter whether I've zoomed into the image or zoomed out of the image. Okay. I realize this is a little bit hard to follow. So this is why I have to kind of go back and look at the book a little bit, because this is really one of the more mathematical ideas of the class. And so doing it in 20 minutes is not going to be so easy. You have to kind of go back and put a little bit of reading in. Okay, but I just want to get the main idea across. Okay. Now, okay. So let me pause and ask, despite my hand waving, are there questions about the kind of concept? Hopefully the concept is good, right? That I want to make sure that large features do not automatically overwhelm small features. That's kind of the idea. Okay. And so kind of what I would do is I would typically, so this k, the reason that I'm using this k is that, typically when I'm considering different so the idea is that when I'm considering different levels of scale, I'm trying to do it in such a way that everything depends on one kind of basic sigma. So it's like saying at the finest scale of the image, the highest resolution image, I choose a little Gaussian width, right? And then from then on, all of my other Gaussians that get wider and wider to find larger and larger scale features are just multiples of that original sigma, okay? That's what this is saying, is that, for example, I might choose 4 to, or I guess we learned that. So say I choose 1 pixel, 2 pixels, 4 pixels, 8 pixels. So it's like saying that there's this, multiples of scales. And the same way, usually I tie the window size, the integration sigma, to my derivative sigma by some factor. So everything is basically building off of one original Gaussian. And again, part of this is for computational efficiency. The idea being that what I could do is, instead of building Gaussian windows that were bigger and bigger, so it's like saying that if I were to take this and convolve it with a little Gaussian, and then I were to take this and convolve this with a Gaussian that's twice as big, I could get fundamentally the same result by making an image that's twice as small and convolving it with the same Gaussian, right? So the idea is that what I'm doing is I can get some computational gains by, instead of making Gaussian filters that get bigger and bigger, I can just make the image smaller and smaller and apply the same Gaussian filter every time, right? So that's kind of the idea behind using this decomposition of scales in such a way that if I reduce things by a factor of k, I can basically reduce the image by a factor of k instead of increasing the scale of the Gaussian. Because as I make bigger and bigger filters, it takes more and more effort to actually filter those pixels in the image, and so why would I not save myself time by just making the image smaller and using the same size Gaussian? That's kind of the idea. Okay, so imagine that I've done all this decomposition, right? So now what I can do is I can say, okay, at every possible scale, I can find features that have a Harris measure that is sufficiently large at a given scale. Right now I'm really comparing apples to apples. The problem is if I do that, I might be in the situation like this, where it's like, say, okay, maybe if this feature was really good, maybe it would be significant at a whole bunch of scales, right? what I want to do in some sense is I want to choose the best one, right? I want to say, okay, you feature, what is your natural best scale, right? Instead of giving me a whole bunch of responses to different scales, give me one that is really your best, right? So what I could do is I could basically take a maximum in the scale direction, right? Give me the one scale that, given that I've passed the test at this pixel, what is the one that makes the most sense, okay? And so to do that, right, that kind of corresponds to this picture that I'm drawing here, right? What I want to do is have a measure on the x-axis here, what I have is changing the scale, turning up the scale. And on the y-axis, what I have is a measure of how good the feature is at that scale. And here what I've shown is I'm picking the maximum value of this kind of goodness function. And here the maximum value corresponds to the radius of the circle, and here the maximum of this value corresponds to the radius of that circle. And you can see that using this approach, I find the circle radii that kind of match up and give me the same apparent set of pixels, right? And so you can see that even though I've zoomed in the image maybe 3 times from here to here, the scale that I've chosen as the best one is also multiplied by 3 times going from here to here, right? So the million-dollar question is, what is the number that I'm plotting on this y-axis, right? What is the number that I'm using to find the maximum of, okay? And let me tell you what that is. So to kind of find what I would call characteristic scale of a feature, we use what's called the normalized Laplacian. So let me just write down what that is. This should be familiar to you now from looking at lots of Poisson equation stuff. So basically what it is it's the derivative of the Gaussian. It's like the Laplacian of a Gaussian. Applied to the image. So this here is like the Laplacian of the Gaussian. Sometimes it's called LOG. And so you were asking before, there was a question about where the second derivatives come in, right? So here's a place where the second derivatives come in. And again, let's not make too much of a deal of this. This is basically just kind of like saying that this, there's a whole bunch of commutativeness going on with these operators, right? So this is like saying I take the Gaussian and I find the Laplacian of that, and I apply that to the image I. That's kind of like, again, something that is finding significant edges of the image smooth at a certain scale. That's all that what's happening. And so what I'm trying to do is, this sigma squared, again, comes from the normalization process that we talked about a little bit earlier. And that means that I can kind of say, okay, at what scale are the edges of the image the most significant, right? That's kind of the right way to interpret this equation. It's like saying that, if I didn't have the Gaussian at all and I just did the Laplacian of the image, and I normalized it in a way that accounted for the size of the box I was caring about, that would be kind of like saying, okay, so at what scale do I think that the edges of the image are most significant? This Gaussian adds some additional smoothing to the whole process to make it a little more robust. Okay. And so this whole thing leads to what are called Harris-Laplace features. And so basically the idea is, find multiscale Harris corners, and I only keep them if the normalized Laplacian is locally maximum at the detected scale. Right? That's kind of like saying that not only do you have to pass the threshold, but you also have to be good in terms of being the edgiest, being the most significant scale that you can be at. Okay. And so let me just show you a picture to illustrate that idea. So here's one image, right? And here's another image that is taken from a different perspective and slightly zoomed in, I guess, right? So you can see these are not exactly the same perspective, nor are they the same resolution. And here is a comparison of detecting these Harris-Laplace features. And so what should I be taking home from this image? Well, number one, I should be seeing that I'm detecting a lot of the same features, right? So for example, here, I'm detecting all these blobs, these wooden, these square posts in the zoomed in image. I didn't detect all of them over here, but the ones I did detect, if I think about the size of the circle basically matches up with the apparent size of the circle over here, right? So physically, these circles are bigger in terms of the number of pixels that they encompass, right? So these may be 20 pixels wide, and these may be only 10 pixels wide. But if I look at this circle here, I can see that it is just almost touching its, the blocks on either side of it. And the same thing is true for these circles up here, right? They're about the same apparent size. Same thing with something like this feature here that's on the edge of this lantern, right? So if you think about the pixels that are included in this circle, they're basically the same apparent pixels that are included in this circle, even though this circle is a lot larger, right? So this is kind of the virtue of these detected features, is that now I have some promise of being able to match up these things because I've got the same kind of content enclosed in that circle, right? That's kind of the idea that we're going for. And again, I detected these exactly using the method I just told you, okay? So again, one of the homework problems, right, is to actually make a picture that looks similar to this, or actually maybe more like similar to this, okay? So I want you to take an image, and then I want you to zoom in on it. And so let's not worry about the detection part. So all I'm really asking you to do is to click on a feature in one image and compute this plot in the bottom of the screen, right? So basically you should be able to, for a given click, make a plot that looks like this that corresponds to, this function as I change sigma, right? And you should get something that locally maxes out at a natural scale. And then as you zoom in, the local max should be basically the same apparent set of pixels, right? So don't worry necessarily about computing the whole multiscale Harris matrix. You don't have to do that. All you have to do is compute this plot as a function of sigma and kind of verify that it works. And so in order to do that, you're going to figure out what the formula for a Gaussian is, take the double derivative, which you can do with Wolfram alpha or something like that, or by hand if you're old school like me, and then use that as a filter that you apply to the image at that point and get a number and then plot that thing. So that's the do-it-yourself problem for the week, is seeing if you can make this idea behind scale covariance work. Okay. One more thing I want to get across before the end of the lecture. Okay. So looking back at this equation, what we see is fundamentally a Gaussian that we are taking the Laplacian of, like the edges of a Gaussian, right? Summing the second derivatives of a Gaussian. Okay, so it turns out that is also a viable way of finding features, right? So what was asked earlier is, well, why not use second derivative information? So this would also be a perfectly valid way to detect features. And so actually, use the Laplacian of Gaussian as a feature detector. And this one is a little bit different in the sense that it uses second derivatives of the image instead of first derivatives. And the idea is very simple. Basically, all I have to do is simply select x, y, and scale that maximize this normalized Laplacian in all 3 dimensions. And these are called, Laplacian of Gaussian features. Pretty straightforward. And if you look at kind of the kinds of features that that comes up with, I believe I have a picture. So like the response of that is something like what you see in this lower left-hand corner. Okay, so here, this is a picture of a plate. You can see there are a bunch of cornery things and there are a bunch of blobby things at different scales. And so here you can see that what's happening is that this Laplacian of Gaussian feature detector is picking up on most of the blobby stuff in the image. And this is a few tomatoes, I guess. This is also picking up on some edgy features that are actually probably not so good. Like it's picking up stuff along the chopsticks that we would like to avoid, right? And so I'll talk in a second about how we can get rid of that stuff, okay? But basically the message I want to get across is that, this Laplacian Gaussian is another standard way of doing features. And so once you dig into this, right, you will find lots of comparisons between different feature detectors for different purposes, right? So at this point, you're probably like, well, why would I choose one over the other? Well, it depends on your application, right? If you're doing something where you're just doing like real-time robotic vision and you want to have a robot that is slowly moving forward and matching features between different views, well, the Harris corners might be just fine, right? But if you want to have 2 images at different resolutions from different perspectives, well, then maybe you want to use something like LOG features that may be more robust. And so we're going to talk, again, next time a little bit more about SIFT. So SIFT is made to be a little bit more what you call scale and rotation invariant. So let me conclude this lecture by talking about what exactly is going on inside SIFT. And so SIFT, is like a super popular feature detector and descriptor in vision. And so again, I want to kind of decouple the detection part from the description part. So let's just talk about detection right now. So what is a SIFT feature detector doing? Basically all it is it's an approximation to the Laplacian of Gaussian. And it uses differences of Gaussians instead. So sometimes you hear these called DOG, for difference of Gaussian. And so why does that work? I guess it's easiest just to show you a picture. So here, basically, this upper left-hand picture is a Gaussian, and the lower left-hand is the Laplacian of the Gaussian, right? That's like the double derivative of the Gaussian, right? And so if I look at this shape of this function here, I can get a very similar shape by saying, okay, take a Gaussian, take a slightly wider Gaussian, and look at the difference between those two things. And it turns out that the difference of those two Gaussians looks a lot like the Laplacian, right? So actually, why is this good? Well, it's a little bit more computationally good, right? Because instead of actually having to take the double derivative of anything, all I have to do is take the difference between two things, and that's a lot easier, right? And so the observation was that you can show that the difference of Gaussians mathematically is pretty close to a Laplacian of Gaussian, okay? And you can read in the book about why exactly that turns out to be true. But that's all that's happening, is that the DOG is not like some super new kind of detector. All it is an approximation to this LOG, which you already knew was kind of a good feature detector. So that's what's happening for SIFT. And there are also a couple of, there's a lot of secret sauce in SIFT about how it does this whole computation efficiently, right? And so let me just show you a picture here. This is really more like what's going on in SIFT. If you ever read a SIFT paper, you're going to see a picture that looks kind of like this. So the idea is that what SIFT is doing is it's taking Gaussian images, Gaussian filters of the image. So here's like a Gaussian at a certain scale processing the image. So this is like a blurry image. This is a slightly blurrier image, a Gaussian that has a slightly bigger sigma. And then I look at the difference between those two Gaussians, that's this gray image, right? So that's the DOG detector, right? So what SIFT is doing is as I keep on blurring the image, I keep on looking at the differences between adjacent Gaussians, and then this pixel here will be selected as a feature point for SIFT if its response to this DOG is bigger than all of its neighbors, both in space and time, right? So this is kind of like similar to using LOG features where I'm looking at something that has to be maximum both in X and Y and also in scale, right? And so the secret sauce partially has to do with, as I keep on blurring this image, right, the image is getting obviously blurrier and blurrier, right? And these Gaussian, these Gaussian filters are getting wider and wider, right? And so at some point, when the Gaussian filter gets a little bit too big, what we do is we downsample all the images and start back up again with basically the same Gaussian scale as I started with, but applying it to a slightly smaller image. This is a computationally efficient way of doing the computation, because now, instead of applying some massive Gaussians to the image, I'm applying the same set of smaller Gaussians to increasingly smaller images, right? So I keep on going down and down and down, making the image smaller and using the same set of nice small Gaussians. And so every kind of bracket here where I have the image at the same actual resolution is called an octave. And so you read about octaves inside SIFT. That's what's happening here. And so there's a little bit of magic to making sure that I don't have to worry about comparing pixels across different octaves. You can read about the details of how that works. There's also something that's kind of good about once I've found a candidate feature, I do a little bit of interpolation to find the best possible location for that feature point, which may not be an integer location on the pixel grid. So basically, there's like a little bit of interpolation to say, okay, instead of choosing 20, 30, can I do a local fit to the image to get a pixel that's centered at 20.2, 29.8, something like that, where there's a little bit of an extra sub-pixel fit to make sure I get as good of a pixel as possible. And then finally, there's a little bit of filtering. So basically, this here on the left is like the raw responses of a difference of Gaussian detector without any sort of filtering process. But like I said before, the Laplacian of Gaussian, which is basically what this is approximating, responds to edges. And so, for example, here, we still have this issue where there's all this stuff detected on chopsticks. And so what you do here to get the final DOG features is you throw stuff out that is too close to being a linear feature. And from that, you can kind of tell whether a feature is linear or not by looking at, again, this eigenvalues of a special 2x2 matrix. And you can say, okay, well, if one of these eigenvalues is too small, I can throw it out. Again, the details are in my book and in the original SIFT paper. And so, again, for you guys, well, let me just pause and say, so at the end of the story, what I get actually from the DOG detector corresponds to basically nice-looking features, right? So what I see is that many of the blob-like things in this image have been detected, and furthermore, the effective size of the feature, the blob size, kind of matches up with how important the features seem to be. So for example, the circles that are at the tips of these spikes are the finest detected features. The ones that are around the circumference of the plate are a little bit bigger, and the tomatoes are even bigger still, right? And the nice thing about the way that SIFT works and the way the DOG detector works is that if I were to make this image twice as big, I would get circles that appeared to be the same way in the bigger image, right? So they have this kind of nice scale covariance property, right? In the sense that the scales I get would be the appropriate multiple of how big the image is, right? So I think this is a good place to stop. So basically, again, to really understand the mathematical underpinnings of all this stuff, I appreciate it takes some time and it takes some reading and it takes some thought, right? But hopefully the key ideas are here, right? And so again, obviously anyone can just download the SIFT library and run it on an image, but at least kind of now you know what you're getting, right? And so next time I want to start by talking about a couple other non-SIFT-y kind of features just as a cleanup, and then talk about how do I take the pixels that are implied by the scale that I get and assign them a descriptor so that if I have a descriptor between what I saw in one image and another image, I can match those things up and get matching features, which is really the whole point of this whole process. So, question before we go?
Yeah, it just seems in the SIFT output, it seems like there are some places where it gets features that
Yes.
seem
So
like
so last comment is SIFT features are typically not as interpretable as what you see in this picture, right? So if you run SIFT on an image, and that's again one of the homework problems is to try out SIFT on a couple images that you take yourself, you're going to find a lot of features that you don't understand, right? Like, why did it choose a feature here? The reason that this looks as good as it does is because this is a relatively simple geometric image, but again, you might ask, so why is this a good feature, right? This blob in the middle of nowhere. Well, again, kind of the way I think about it is that, you know, it's not necessarily true that this feature is only characterized by what's inside the circle that I drew, right? The circle that I drew is kind of like the scale that I chose, but there are pixels from outside the circle that are contributing to that making a good feature. And so probably what's happening here is that the fact that there's like this strong tangent between this chopsticks and between this tomato are probably making this empty region a good feature because of what's around it, not because what's inside of it, right?
And that's very similar to the other spot that's between three dots a little bit.
Yeah, there's one over here. Where is it? Oh, yes, like this. This is also probably happening because of that, right? But if you apply SIFT to a real image, you're going to come up with a lot of features that are like, I don't understand why this is happening. But again, that's the whole point of these descriptors, or just detectors, is the detectors are not there to provide you with obviously interpretable, semantically useful points. They're there to help you with mathematically findable regions, right? And that's why they may not make sense to you as a human. You wouldn't depict them out yourself, but they turn out to be very robust for matching. So we'll talk more about that descriptor process and why they're good for matching next time.
Nice.
Okay. See you on Tuesday. Just one second. I can never close this when I want. Why do I suck?